a point in space where light cannot escape, where the rules of reality break down, where time itself stops. Black holes are not holes at all. They are objects, real objects, made of matter so densely packed that gravity becomes absolute. Nothing that crosses a certain boundary can ever return. Not light, not matter, not information. This boundary has a name: the event horizon. For most of human history, black holes existed only in mathematics, in equations that seemed too strange to be real. In 1783, an English country parson named John Michell imagined them first. He called them dark stars, objects so massive that light itself could not escape their pull. The idea was forgotten, lost for nearly 2 centuries. In 1915, Albert Einstein published his theory of general relativity, a new way of understanding gravity, not as a force, but as a curvature of space and time. Within months, a physicist named Karl Schwarzschild found a solution to Einstein's equations, a solution that described something impossible, a point where matter could collapse forever, where the mathematics went infinite. Einstein himself didn't believe it could be real. Neither did most scientists. For decades, black holes remained theoretical curiosities, monsters that lived only on paper. Then, in 1964, a rocket detected something strange, an intense source of X-rays in the constellation Cygnus, brighter than anything that should exist. Scientists called it Cygnus X-1. By 1971, astronomers had pieced together what it was: a bright blue supergiant star orbiting something invisible, something with a mass far too large to be anything known. The invisible object was pulling material from the star, gas spiraling inward at tremendous speeds, heating to millions of degrees, screaming in X-rays before vanishing forever. This was the first black hole ever found, the first proof that these objects were not just mathematics, they were real. Black holes come in different sizes. Stellar mass black holes form when massive stars die, when a star at least 10 to 20 times the mass of our Sun exhausts its fuel. The core collapses. In less than a second, matter that once filled millions of kilometers compresses into a point. The star's outer layers explode outward in a supernova, but the core keeps collapsing. Nothing can stop it. What remains is a stellar mass black hole, typically 3 to 20 times the mass of the Sun, concentrated in a region smaller than a city. The Milky Way likely contains 100 million of these objects. Most are invisible, silent, drifting through the galaxy unseen. Then there are the supermassive black holes, monsters millions or billions of times more massive than the Sun. Every large galaxy appears to contain one at its center, including our own. At the heart of the Milky Way, 26,000 light-years from Earth, sits Sagittarius A star, a supermassive black hole with a mass 4 million times that of our Sun. We cannot see it directly, but we can see stars orbiting around it, moving at speeds that reveal the invisible mass at the center. Some stars complete their orbits in just 16 years, whipping around the black hole at nearly 2% the speed of light. For decades, scientists studied black holes indirectly, through the radiation from falling matter, through the movements of nearby stars, through mathematical models. But no one had ever seen one. Then, in 2019, something changed. A network of 8 radio telescopes spread across the Earth, from Hawaii to Antarctica, from Chile to Spain, working together as one giant telescope the size of the planet. The Event Horizon Telescope, named for the boundary it sought to image. On April 10, 2019, the collaboration released an image, the first photograph of a black hole. Not the black hole itself, but its shadow. The shadow appears as a dark circle surrounded by a bright ring of glowing gas. The black hole sits at the center of a galaxy called Messier 87, 55 million light-years from Earth. Its mass is 6.5 billion times that of the Sun. Its event horizon stretches 40 billion kilometers across. The ring of light is gas, superheated to billions of degrees as it spirals toward the event horizon, moving at nearly the speed of light. The shadow is larger than the event horizon itself. Because the black hole's gravity bends light from behind it, creating a dark region 2.5 times wider than the actual boundary. This image confirmed what Einstein predicted over a century ago. The shadow is round, just as general relativity said it should be. Within 10% accuracy, the universe had revealed one of its darkest secrets, and humanity had finally seen what was once thought impossible to see. But what exactly is a black hole? To understand, we must think about gravity differently. Gravity is not a force pulling objects together. It is the curvature of space and time itself. Massive objects bend the fabric of space-time around them, like a bowling ball placed on a stretched sheet. The more massive the object, the deeper the curve, the steeper the slope. A black hole is where this curvature becomes infinite, where the slope becomes so steep that nothing can climb back out. Not even light, traveling at 300,000 kilometers per second. The boundary where escape becomes impossible is the event horizon. Cross this line, and your fate is sealed. You will fall toward the center, forever. The event horizon is not a physical surface. It's not made of anything. It's simply a point of no return, a mathematical boundary in space-time. For a black hole with the mass of our Sun, the event horizon would be about 3 kilometers across. For one with 10 solar masses, 30 kilometers. For Sagittarius A star at the center of our galaxy, it stretches 12 million kilometers. But the event horizon is not the end of the story. At the very center of every black hole lies something stranger still: the singularity. This is where all the mass of the black hole exists, according to general relativity, compressed to a point of zero volume. Infinite density, infinite curvature of space-time. A place where the mathematics breaks down completely, where our understanding of physics ends. No one knows what happens at the singularity. The equations produce infinity, which in physics usually means the equations themselves are incomplete. Perhaps quantum mechanics provides an answer. Perhaps something else we haven't discovered yet. Black holes spin, almost all of them. They retain the angular momentum of the stars that formed them. A spinning black hole drags space-time around with it, like water swirling down a drain, but far more extreme. Near the event horizon of a rapidly spinning black hole, space-time itself is pulled around at tremendous speeds, creating a region called the ergosphere. Within the ergosphere, Nothing can stand still. Everything must move in the direction of the black hole's rotation. Even light. The fastest spinning black hole ever measured rotates more than 1,000 times per second. Its event horizon is nearly moving at the speed of light. In contrast, our Sun rotates once every 27 days. This extreme rotation affects the shape of the event horizon, turning it from a perfect sphere into a flattened ellipsoid. And it allows for something remarkable: energy extraction. A process called the Penrose process, named after physicist Roger Penrose. By dropping matter into the ergosphere in just the right way, it's theoretically possible to extract energy from a spinning black hole. More energy than you put in. This has never been observed, but the mathematics says it's possible. Black holes are not cosmic vacuum cleaners. This is a common misconception. They don't suck everything nearby into oblivion. Their gravity from a distance is no different from any other object of the same mass. If the Sun were replaced by a black hole of equal mass, Earth's orbit would remain unchanged. We would freeze in the darkness, but we would not fall in. The danger comes only when you approach the event horizon, when you enter the region where escape velocity exceeds the speed of light. And if you did fall toward a black hole, something strange would happen. Something called spaghettification. A real scientific term.
As you fall feet first toward the black hole, gravity pulls harder on your feet than your head. The difference becomes extreme. Your body would be stretched vertically, compressed horizontally, pulled into a long, thin strand, like a piece of spaghetti. For a stellar mass black hole, this would happen long before you reached the event horizon. You would be torn apart in seconds. But for a supermassive black hole, the event horizon is so large that tidal forces are weaker. You could cross the horizon intact. Not that it would save you. Once inside, you would still fall toward the singularity, with no possibility of escape. From the outside, something else strange would occur. As you fell toward the event horizon, time itself would slow down for you. From the perspective of someone watching from far away, your descent would appear to take forever. You would move slower and slower. The light from your body would shift toward red, becoming dimmer and dimmer, until finally, frozen at the event horizon, you would fade from view. But from your own perspective, nothing special would happen at the event horizon. You would fall through in finite time. This is one of the paradoxes of black holes. What you experience and what others observe are fundamentally different. Time near a black hole behaves in ways that defy intuition. This is not science fiction. This is general relativity, confirmed by observation. And it leads to one of the most profound questions about black holes. What happens to information that falls in? In quantum mechanics, information cannot be destroyed. It can be scrambled, hidden, transformed, but never lost. Yet a black hole appears to violate this principle. Matter falls past the event horizon. All its information about position, velocity, quantum state, gone. Or is it? In 1974, physicist Stephen Hawking discovered something unexpected. Black holes are not completely black. They emit radiation. This radiation comes from quantum effects at the event horizon, virtual particles that normally appear and disappear in pairs. Near the event horizon, one particle can fall in while the other escapes. The escaping particle becomes real, carrying energy away from the black hole. To an outside observer, the black hole appears to glow, very faintly. The smaller the black hole, the hotter this radiation. For a stellar mass black hole, Hawking radiation has a temperature of billionths of a degree above absolute zero, far colder than the cosmic microwave background. These black holes absorb more radiation than they emit. They grow. But a very small black hole would be hot, would radiate strongly. And over immense timescales, trillions upon trillions of years, even large black holes would evaporate, slowly losing mass through Hawking radiation, getting smaller, hotter, until, in a final burst of energy, they would vanish completely. This creates a paradox. If a black hole can evaporate, what happens to the information that fell in? Is it lost when the black hole disappears? Or is it somehow encoded in the Hawking radiation? This question has occupied physicists for 50 years. It's called the black hole information paradox. Some believe the information is preserved in subtle correlations in the radiation. Others suggest it's stored at the event horizon itself. Still others propose that our understanding of space-time at the quantum level is incomplete. The paradox remains unsolved. Black holes challenge everything we think we know about the universe. They sit at the intersection of quantum mechanics and gravity, two theories that have never been successfully unified. To fully understand what happens inside a black hole, we would need a theory of quantum gravity, a theory that doesn't yet exist. Perhaps the singularity is not truly a point of infinite density. Perhaps at the quantum scale, something else happens. A quantum bounce. A connection to another region of space-time. Something we cannot yet imagine. Meanwhile, astronomers continue to discover black holes throughout the universe, using different methods, different wavelengths of light. When matter falls into a black hole, it forms an accretion disk, a swirling disk of gas and dust.
Friction within this disk heats the material to millions of degrees. It glows in X-rays. This is how we detect most stellar mass black holes, by the X-rays from their accretion disks. Some black holes pull material from companion stars, stripping gas away in long streams that spiral inward. These are called X-ray binary systems. The X-rays flicker and pulse as hot spots in the disk rotate around the black hole. By studying these patterns, astronomers can measure the black hole's mass, its spin, the structure of space-time around it. Supermassive black holes create even more dramatic displays. The accretion disks around these giants can outshine entire galaxies. Powered by millions or billions of solar masses falling into the black hole over millions of years. Some of this material doesn't fall in. It's channeled into enormous jets, beams of particles and radiation shot out from the poles of the black hole. These jets can extend for hundreds of thousands of light years, moving at nearly the speed of light. They're powered by the black hole's rotation, by magnetic fields twisted into corkscrews around the event horizon. The exact mechanism is still being studied, but observations confirm these jets exist. They're some of the most energetic phenomena in the universe. In 2015, another method of detecting black holes became reality: gravitational waves. When two black holes orbit each other, they create ripples in space-time itself. As they spiral closer, these ripples grow stronger, moving outward at the speed of light. On September 14, 2015, two detectors in the United States measured these ripples, for the first time in history. The signal lasted a fraction of a second, a chirp in the data, but it told a story. 1.4 billion years ago, two black holes collided, one with 36 times the mass of the Sun, the other with 29.
They merged into a single black hole, 62 solar masses. 3 solar masses were converted directly into gravitational wave energy in a tenth of a second. More power than all the stars in the visible universe combined, released as ripples in space-time. Since then, hundreds more gravitational wave events have been detected. Black hole mergers, neutron-star collisions, each one teaching us something new. The masses of black holes, how often they merge, how they spin. Gravitational waves have opened a new way of observing the universe, a way that doesn't rely on light. And it's revealed something unexpected. Black holes are more common than anyone thought, merging more frequently, spanning a wider range of masses, including intermediate mass black holes, objects weighing hundreds to thousands of solar masses. These were once purely theoretical. Now we know they exist. The universe is full of black holes. At the centers of galaxies, wandering through interstellar space, the closest known black hole to Earth is called Gaia BH1, 1,560 light-years away. It sits in a binary system with a sun-like star, invisible except for the way it tugs on its companion. The most massive black hole ever observed weighs 66 billion times the mass of the Sun. It sits at the center of a distant quasar. The most distant black hole detected formed just 400 million years after the Big Bang, when the universe was only 3% of its current age. How it grew so large so quickly remains a mystery. Black holes may have played a role in shaping galaxies themselves. Almost every large galaxy contains a supermassive black hole at its center. The relationship is not random. The mass of the central black hole correlates with the mass of the galaxy's bulge, with the velocity of stars in the galaxy, as if the black hole and the galaxy grew together, influencing each other's evolution over billions of years. When galaxies collide, their central black holes eventually merge, creating gravitational wave events detectable across the universe. These mergers may trigger bursts of star formation, reshape the structure of the merged galaxy. The energy released can heat gas throughout the galaxy, preventing it from cooling and forming new stars. In this way, black holes regulate their own food supply. Some supermassive black holes are relatively quiet.
Like Sagittarius A star at the center of the Milky Way. It consumes matter slowly, barely glowing. But others are voracious. These are called active galactic nuclei, quasars. They consume the equivalent of multiple suns per year. Their accretion disks glow so brightly they can be seen across billions of light-years, outshining 1 trillion stars. The most luminous quasars in the early universe were powered by black holes billions of times more massive than the Sun, growing rapidly in the young cosmos. How they grew so large so quickly is still debated. Perhaps they formed from the direct collapse of massive gas clouds, perhaps from the merger of many smaller black holes. Or perhaps the early universe allowed black holes to feed faster than we thought possible. In 2022, the Event Horizon Telescope released a second image, this time of Sagittarius A star, the black hole at the center of our own galaxy. The image shows the same bright ring surrounding a dark shadow. But capturing this image was harder. Sagittarius A star is much smaller than the black hole in M87. Material orbits it in minutes rather than days. The bright spots in the accretion disk change position faster than the telescopes can observe. It took years of data analysis to create a stable image. But the result confirmed what astronomers expected: another black hole shadow.
another test of general relativity, another piece of evidence that these objects truly exist. Black holes also raise questions about the nature of information. In the 1970s, physicist Stephen Hawking discovered that black holes emit radiation. Quantum effects near the event horizon allow particles to escape. The black hole slowly loses mass. Over unimaginable timescales, trillions upon trillions of years, a black hole could evaporate completely. This creates a paradox. If matter falls into a black hole, it carries information, the quantum states of every particle. When the black hole evaporates, where does that information go? Is it lost forever? Or is it somehow encoded in the Hawking radiation? This question has occupied physicists for 50 years. It's called the black hole information paradox. Some believe the information is preserved in subtle patterns in the radiation. Others suggest it's stored at the event horizon itself. Still others propose that our understanding of quantum mechanics and gravity is incomplete. The paradox remains unsolved. To fully understand black holes, we need a theory that unifies quantum mechanics and general relativity. A theory of quantum gravity. Such a theory doesn't exist yet. String theory offers one approach, loop quantum gravity another. But none have been confirmed by observation. The singularity at the center of a black hole may be where quantum gravity becomes essential. Perhaps there is no true singularity. Perhaps at the smallest scales, something else happens. A quantum bounce, a bridge to another region of space-time. Something we cannot yet imagine. Black holes also affect time in profound ways. The closer you get to a black hole, the slower time moves, relative to someone far away. This is called gravitational time dilation. It's not a trick or an illusion. If you orbited close to a black hole for what felt like 1 year, decades might pass for someone watching from Earth. The effect becomes extreme near the event horizon. From the outside, an object falling toward the horizon appears to slow down, to freeze. Its light shifts toward red as it dims, eventually fading from view. But from the falling object's perspective, nothing special happens at the horizon. It crosses in finite time. This is one of the strange paradoxes of black holes. What you experience and what others observe are fundamentally different.
Black holes may also be connected to wormholes. Solutions to Einstein's equations suggest that some black holes could contain tunnels through space-time, bridges to other locations in the universe, or even other universes. These are called Einstein-Rosen bridges, but they're unstable. They would collapse before anything could pass through. And even if they didn't, the tidal forces would destroy anything attempting the journey. For now, wormholes remain theoretical. No evidence suggests they exist in nature. The study of black holes has transformed our understanding of the universe. They've confirmed Einstein's predictions about gravity, revealed new physics at the intersection of quantum mechanics and relativity. They've shown us that the universe is stranger than we imagined, more extreme, more beautiful. And there is still so much we don't know. How do supermassive black holes form in the early universe? What happens at the singularity? Can information truly escape a black hole? Do black holes play a role in dark matter? In dark energy? Every answer reveals new questions. In the coming years, new telescopes will study black holes in greater detail. The Event Horizon Telescope continues to improve, adding new observatories, observing at shorter wavelengths. Future space-based gravitational wave detectors
will detect mergers of supermassive black holes, events invisible to ground-based instruments. The James Webb Space Telescope is already finding black holes in the early universe, pushing back the timeline of when these objects first formed. Each observation brings us closer to understanding, closer to solving the mysteries. Black holes also play a role in the evolution of galaxies. Almost every large galaxy contains a supermassive black hole at its center. The relationship is not random. The mass of the central black hole correlates with the mass of the galaxy's bulge, with the velocity of stars in the galaxy, as if the black hole and the galaxy grew together, influencing each other's evolution over billions of years. When galaxies collide, their central black holes eventually merge, creating gravitational wave events detectable across the universe. These mergers may trigger bursts of star formation, reshape the structure of the merged galaxy. The energy released can heat gas throughout the galaxy, preventing it from cooling and forming new stars. In this way, black holes regulate their own food supply. The relationship between black holes and galaxies raises profound questions. Did the black hole form first, seeding the galaxy around it? Or did the galaxy form first, with the black hole growing at its center? The answer may be both, in different ways at different times. In the early universe, some black holes may have formed from the direct collapse of massive gas clouds. These seed black holes then attracted more matter, growing into the supermassive objects we see today. But the process is still not fully understood. Black holes also affect their surroundings through feedback. The jets and winds from active black holes can push gas out of galaxies, preventing star formation across vast regions. This feedback may explain why the most massive galaxies stopped forming stars billions of years ago. The central black hole grew so large and so active that it shut down star formation entirely, starving itself in the process. These galaxies are now quiet, filled with old red stars, their black holes dormant. Some black holes wander through space alone, ejected from their galaxies during mergers, or simply drifting between stars. These rogue black holes are difficult to detect. They have no accretion disks, no companion stars. They're invisible against the darkness of space. But they may be common. Millions of them scattered throughout the Milky Way. Silent, hidden, waiting. The closest known black hole to Earth is 1,500 light-years away, far enough that we're in no danger, but close enough to study in detail. It orbits a sun-like star, pulling on it gravitationally. The star wobbles in its orbit, revealing the presence of its invisible companion. This is how most stellar mass black holes near Earth are discovered, through their gravitational influence on visible stars. The universe may contain billions of black holes. From stellar mass objects to supermassive giants, each one a laboratory for extreme physics, each one a mystery. And at the center of each one, the singularity, a point where our understanding breaks down completely, where the laws of physics as we know them cease to apply. Perhaps this is where the universe hides its deepest secrets. Perhaps this is where new physics waits to be discovered. Black holes challenge everything we think we know about reality. They force us to confront the limits of our theories, the boundaries of what we can observe and understand. They remind us that the universe is far stranger than our everyday experience suggests, that space and time are not fixed and absolute, that gravity is not a force, but a curvature, that matter and energy can be compressed beyond imagination, and that at the most extreme limits, even light cannot escape.
Yet for all their strangeness, black holes are real. Not thought experiments or mathematical curiosities, real objects that shape the cosmos, that forge the structure of galaxies, that merge in cosmic collisions, producing ripples in space-time itself, that consume stars and gas and matter, that glow in X-rays and radio waves, that cast shadows against the light of their surroundings. Shadows we have now seen. The story of black holes is far from over. New discoveries arrive regularly. New observations challenge our understanding. New questions emerge with each answer. How do the most massive black holes form so early in the universe? What truly happens at the singularity? Can information escape from a black hole? Do wormholes exist in nature? What role do black holes play in the fabric of space-time? These questions drive research forward. They inspire new telescopes, new experiments, new ways of observing the universe. And with each new observation, we come closer to understanding, closer to unraveling the mysteries, closer to comprehending the most extreme objects in existence. Objects where space and time lose their meaning, where gravity becomes absolute, where the universe reveals its darkest nature. In a sense, black holes are windows, not into other dimensions or universes, but into the fundamental nature of reality itself. They show us what happens when matter is pushed to its limits, when gravity overwhelms all other forces, when space-time curves back on itself, when the equations that describe our universe encounter infinity. And in confronting these infinities, we are forced to seek new understanding. Perhaps one day we will have a complete theory of quantum gravity, a theory that unifies the very small with the very large, that explains what happens at the singularity, that resolves the information paradox.
That tells us whether black holes truly destroy information or preserve it in ways we don't yet understand. Until then, black holes remain among the greatest mysteries in science, objects that captivate our imagination, that challenge our understanding, that remind us how much we have yet to learn. They are nature's most extreme laboratories, testing the limits of physics in ways no human experiment ever could. And in studying them, we learn not just about black holes, but about the universe itself, about gravity and space-time, about matter and energy, about the fundamental laws that govern everything. And perhaps, in time, about the nature of reality at its deepest level. Black holes also teach us humility. They remind us that our understanding is incomplete, that the universe contains phenomena we cannot fully explain, that there are limits to what we can observe, boundaries beyond which our instruments cannot see, and questions we may never fully answer. But this does not stop us from trying, from building better telescopes, from developing new theories, from pushing the boundaries of what is possible. The pursuit of knowledge about black holes continues, in observatories around the world, in gravitational wave detectors listening for collisions, in supercomputers simulating the behavior of matter near event horizons, in the minds of physicists wrestling with paradoxes, in the data from telescopes pointed at the centers of galaxies, each piece of evidence adding to our understanding, each observation refining our theories. And sometimes, the universe surprises us. A black hole spins faster than thought possible. A merger produces gravitational waves with unexpected properties.
A quasar in the early universe hosts a black hole that shouldn't exist yet. These surprises force us to revise our models, to question our assumptions, to imagine new possibilities. And in doing so, we inch closer to the truth. The study of black holes has already revolutionized physics. It has confirmed general relativity in extreme conditions. It has opened the field of gravitational wave astronomy. It has revealed the connection between black holes and galaxies. It has shown us that space and time are more flexible than we imagined, and it has raised questions that may lead to new theories, new understandings of the universe, new insights into the nature of existence itself. Black holes exist at the intersection of the known and the unknown. They are both real and mysterious, observable yet incomprehensible. We can measure their mass and spin, but we cannot see inside them. We can detect their effects on surrounding matter, but we cannot witness what happens at the singularity. We can photograph their shadows, but we cannot escape their grasp once we've crossed the event horizon. In this way, black holes embody the scientific method itself. We observe what we can. We measure what is measurable. We build theories based on evidence, and we accept that some things remain beyond our reach, at least for now. But the boundaries of the knowable are not fixed. They shift with each new discovery, each new technology, each new idea. And so the exploration continues, into the darkness, into the unknown, into the heart of the most mysterious objects in the cosmos. Black holes, where light cannot escape, where time stops, where the universe hides its secrets, in silence, in shadow, in the infinite curve of space-time. They remain enigmas, puzzles that may never be fully solved. But with each question answered, we understand the universe a little better. We see a little further into the darkness. We grasp a little more of the fundamental nature of reality. And perhaps that is enough. To know that these objects exist, that they shape galaxies and bend space-time, that they challenge our understanding, that they push us to think deeper, to look further, to never stop asking questions about the universe and our place in it. Black holes are not just astronomical objects. They are testaments to the power of human curiosity, to our desire to understand the cosmos, to our willingness to confront the unknown, and to our recognition that some mysteries are worth pursuing, even if they can never be fully understood. In the end, black holes remind us of something profound, that the universe is vast beyond comprehension, that it contains wonders we are only beginning to glimpse, that reality is stranger and more beautiful than we ever imagined, and that there is always more to discover, always more to learn, always more questions to ask. So we continue to observe, to measure, to theorize, to search for answers in the darkness. And in doing so, we illuminate not just black holes, but the nature of the universe itself. One observation at a time, one discovery at a time, one question at a time. The journey continues into the heart of darkness, into the deepest mysteries of existence, where black holes wait, silent witnesses to the birth and death of stars, guardians of secrets we may never fully know, but will never stop seeking to understand. For in seeking to understand black holes,
we seek to understand ourselves, our place in the cosmos, our relationship with space and time, the fundamental nature of reality. These objects of infinite darkness have illuminated so much about physics, about the universe, about the limits of human knowledge, and about the power of human curiosity. The first black hole was discovered in 1971, just over 50 years ago. In that time, we have learned more about the universe than in all previous human history. We have detected gravitational waves. We have photographed the shadow of a black hole. We have watched stars orbit the invisible giant at the center of our galaxy. We have witnessed collisions that shake the fabric of space-time itself. And yet, we are still at the beginning. The mysteries outnumber the answers. The questions multiply with each discovery. But that is the nature of science. Each answer opens new doors. Each solution reveals new puzzles. Each discovery hints at deeper truths waiting to be found. Black holes will continue to challenge us, to push the boundaries of what we think is possible, to force us to question our assumptions, to inspire new generations of scientists. Children who look up at the night sky and wonder. Students who choose to study physics because of a photograph of a black hole's shadow. Researchers who dedicate their lives to unraveling these mysteries. The story of black holes is also the story of human ingenuity, of collaboration across continents, of telescopes working together as one, of data analyzed by thousands of researchers, of theories tested against observation, of mathematics made real, of imagination constrained by evidence, of wonder grounded in science. It is the story of humanity reaching beyond itself, beyond our planet, beyond our solar system, beyond our galaxy, to understand objects so extreme they defy imagination, so massive they bend light itself, so dense they compress infinity into a point. And in understanding them, we understand more about everything, about how galaxies form, about how the universe evolves, about how space and time work, about what is possible in this cosmos we call home, and about what remains forever beyond our reach. The darkness of a black hole is absolute, but it has brought light to our understanding. The mystery is profound, but it has inspired profound insights. The questions are endless, but so is our determination to answer them. Black holes stand as monuments to the extreme, to what happens when nature is pushed to its limits, when gravity becomes irresistible, when matter collapses without end, when time itself bends and breaks. They are the universe at its most intense, its most dramatic, its most mysterious. And we are privileged to study them. The research continues. New telescopes are being built. New detectors are coming online. New theories are being developed. And with each advancement, we see a little further, understand a little more, come closer to answering the deepest questions. What happens at the singularity? Can information truly escape? How do supermassive black holes form so early? What role do they play in the evolution of galaxies? These questions drive the work forward, inspire the next generation,
keep humanity reaching toward the stars, toward the darkness, toward understanding.
And perhaps one day, we will have answers. A complete theory of quantum gravity, a full understanding of what lies beyond the event horizon, a resolution to the paradoxes. Or perhaps some mysteries will remain. Some questions will stay unanswered. Some secrets will be kept by the darkness. But even then, the pursuit will have been worthwhile. For in reaching toward black holes, we have reached toward the infinite. In studying the extreme, we have learned about the everyday. In confronting the unknown, we have expanded the known. And in seeking to understand these objects of darkness, we have brought light to the cosmos and to ourselves. Black holes are more than astronomical phenomena. They are proof that reality exceeds imagination, that the universe contains wonders beyond comprehension. They are testaments to curiosity, to the human drive to explore, to ask questions, to seek truth even when it hides in shadow. From John Michell's dark stars in 1783, to Einstein's equations in 1915, to the first detection in 1971, to gravitational waves in 2015, to the first photograph in 2019, the journey has been long, and it continues. Every observation brings new questions. Every answer reveals deeper mysteries. And that is exactly as it should be. For the universe is not meant to be fully known. It is meant to be explored, wondered at, studied with awe and humility. Black holes remind us that we are small, but our questions are not. Our curiosity is not. Our capacity to understand is not. We stand on a small planet orbiting an ordinary star in one galaxy among billions. Yet we have glimpsed the edge of infinity. We have measured the unmeasurable. We have seen the unseeable. And we will continue, building better instruments, asking deeper questions, reaching further into the darkness. Not because we must, but because we can. Because we are human, and humans explore. The black holes will still be there, bending light, warping time, guarding their singularities. Silent, patient, eternal, waiting for us to understand them a little better. One discovery at a time, one question at a time, one moment of wonder at a time. In the darkness, there is light. In the mystery, there is meaning. And in black holes, there is everything we need to know about reaching beyond ourselves, into the infinite, into the unknown, into the heart of the cosmos, where black holes wait, and where we will always return, seeking, wondering, understanding.